So, okay, problem 1, compute sine pi over 4 and cosine pi over 4. So I see pi over 4, and immediately the first thing that comes to my head is this triangle. Where you have pi over 4, and if that's the case, what are these sides?
1, 1, root 1, 1, root 2.
1, 1, and root 2. Making, let's do sine first. Sine is what over what?
1 over root 2.
1 over root 2, but in general it's opposite over hypotenuse. And so you can choose either one you want, and you'll get 1 over root 2.
And so is cosine.
Cosine happens to be the same here. Happens to be the case that cosine is in terms of sides, it's what over what?
Adjacent.
Adjacent over hypotenuse. And so if you're here, adjacent is 1, hypotenuse is root 2. Or if you're there, adjacent is 1. Hypotenuse is root 2. Either way, you get, in both cases, 1 over square root 2. I could have said pi over 6, or I could have said pi over 7. Whatever, I just chose this one. Now, let's scale the 45, 45, 90 triangle so that the hypotenuse equals 1. Right now, the hypotenuse is equal to what? Root 2. So what do I need to multiply or divide by to scale that thing down so that it's 1?
1 over the reciprocal. 1 over root 2.
And so when I do that, what do I end up with here? Well, that was the point, right? Was so that guy equals 1. And then that divided by root 2 is, well, I guess 1 over root 2. This guy divided by root 2 is 1 over root 2. Okay, so that's all I asked for part 2. Scale it. Right? So we've shrunk it. But check this out. This is the cool thing. Use a scaled one to find sine and cosine. Okay. Sine of pi over 4. Sine is what over what? The opposite over hypotenuse.
It's the same again.
The hypotenuse is 1. So I'm not even going to bother writing it, right? I mean, if I know that hypotenuse is 1, well, I could just say, well, it's whatever that length is right there. Ditto cosine. Pi over 4. Cosine's adjacent over hypotenuse is equal to 1. I don't even need to bother, right? I'm not gonna do this, right? Like that over that, because divided by 1 is just the same thing. So, interesting. And so you might think, well, given any right triangle with any angle right here, if that hypotenuse is 1, well then it doesn't matter what these lengths are, right?
Yeah.
It'll be, if you do sine, you'll get that over, over 1. You'll get cosine, which would be that over, over 1. We'll come back to this in just a minute. But before we do that, all right? And this is, if you'll notice, this is why I call it the 45, 45, 90. I said this when I first introduced this, like day 1, right? Or day 2. I said, we're going to call this the 45, 45, 90 and the 30, 60, 90 triangle. Because it doesn't matter as long as the angle, as long as those angles are the same, it doesn't matter how big you've scaled up or scaled down, all of the trig functions, as we saw last time, are only dependent on one angle. You could think about it as 2 angles because the other angle is also determined, but yeah, so it doesn't matter how you choose to scale it. The values of the trig functions will be the same no matter how much that guy has been scaled or not. Okay, so in your homework, we're going to go over how to do some of these homework problems. Then we're going to get into some new stuff if we have time. But I want you to, we're just basically continuing on with the same thing. We've been using what we talked about last time. We're going to continue building some skills with that. So this is number 12 from the homework. It's not part of the homework because these are odd, right? Yeah, just like last year. This is the kind of thing we're going to do. What we're going to do is find exact values. It says exact values. And anytime they give you that, we're talking about like 1 over the square root of 2. Don't plug that into your calculator and write it like find 1 divided by root 2 and blah. Exact values for x and y. And they're going to give you something like this. Here's a triangle. They're going to give you a measure right here. In this case, it happens to be 60 degrees. They give you this, and they give you that. Now there's two ways you could go about doing this, and I would suggest at first, with at least these, I think it's 11, 13, and 15, I would suggest that you do it both ways. Just both the ways that we're about to do here, so that you get a feel for it and you could see, okay, when is this going to be helpful, when is it not? But I certainly want you to do the harder way too, because when it's not either 60, 30, or 45, or in other words, pi over 6, pi over 4, pi over 3, when it's not one of those, we won't be able to use one of these methods. But since that is this a triangle that we've already done before?
Yes.
Yeah, we know what this is. This is the 30, 60, 90 triangle. And I like to orient it this way. This is just how I like to do it. We know that this is the 60. If this is the case, what are the values we've been using for the sides?
1 root 3 and 2 root 3.
And 2. And so, if we need to scale this guy up to that guy, what do I need to multiply every side by?
Root 3.
Root 3. There you go. And so I'm going to go ahead and do that. I'm going to multiply that by root 3. I'm going to multiply that by root 3. I'm going to multiply that by root 3 to obtain my triangle here, which is root 3, 2 root 3, and 3. And now it's oriented differently, but you could see which is x and which is y.
X is 2 root 3, the hypotenuse.
Yeah, there you go. That's how I would probably do it. I'd say, well, which one's the hypotenuse? The hypotenuse is x. That's the hypotenuse. So this guy must be x, and the other one must be y. So that's one way of doing it. It's very useful and very quick, as you can see. The other way, but the problem is, this only works if you have one of the two triangles we know how to do. Like either if this happens to be a 30, 60, or a 90, I mean a 30, a 60, or a 45, then you could do this. Otherwise, you're going to need to do the harder method, which is the following. So like for instance, if this were 7.5 degrees, I have no idea what
Well, the other one has to be 90 minus 7, like that.
the other one would be. Then we'd know that, but that wouldn't help us because we don't have a triangle that we could scale.
Yeah.
Right? So what we'd have to do, this is why I want you to do this both ways, because this is super useful in a lot of different ways, but in general, that's not going to help us. So what we're going to need to do is this. We need to think of a trig function. So we happen to know what is, like if I told you any of the trig functions, like for instance, if I started off today by saying find sine of 60, like if I said, let's compute sine, instead of pi over 3, if I said, what's sine pi over 6, what would that be?
30 degree.
It would be the 30 degree one, which would be that guy right there.
So it'd be 1 over 2.
We would know that that's 1/2. And so, maybe if it weren't pi over 6, if I could put it as 30 degrees, something like that. And we'd say, okay, I know that. Well, what we could do then is check this out. This happens to be sine 60. Sorry, I'm getting ahead of myself. The idea is this. We could use, since we know what sine of 60 is, what cosine of 60 is, what all of that, we could relate this thing to known values. One thing you might think is to say, well, what about maybe I could find cosine of 60. What's cosine of 60, real quick?
1 over 2.
There you go. Cosine 60 degrees is adjacent over hypotenuse. I'm going to get these out of there because this will be... And what we did here is we multiplied by root 3. I could say, okay, adjacent over hypotenuse, so 1/2. Then you could relate that to this and say, okay, well then, in this case, what is sine of this right here in terms of my variables?
Y over x.
Y over x. Problem is, you have one equation, two unknowns.
But you can make another one.
You could. That's another way you could do it. You could go through and find another one. Or, what I think is infinitely easier, is to say, we've been given a known right here. And so if I choose a trig function that incorporates, say, that one with that one, then I'll have an equation with only one unknown in it. And so what's a trig function that relates this side to that side with respect to that angle?
Opposite over.
Yeah, what's
Sin.
opposite? Sine, please.
Right.
Sine. We are in a church, young man. Sine of that angle, which happens to be 60, is what over what?
3 over x.
3 over x. And now, we can actually compute what sine 60 is. What is sine 60? Right here.
Root 3 over 2.
Root 3 over 2, because it's opposite over hypotenuse. And so we have root 3 over 2 is equal to 3 over x. You could, any way you want to do this.
Doesn't that also only work if it's a 30, 60, 90, or 40?
Yeah, or if it's like, if it happened to be 7.4 degrees, then you could plug that into a calculator.
Oh.
Right, like whatever this happens to be, you could just plug that into your calculator and it'll tell you, 0.2755. And so then you just plug in 0.2755 right there.
Okay.
Now, actually, but another way, when we do another one of these, I'll show you the way that I would normally deal with this. Actually, yeah, for the next part here, when we find y, I'll show you how I usually deal with this. Okay, and so we could do this any way you want. I'm going to bring x upstairs, bring 2 upstairs. 2 times 3 is 6. You guys follow me there? Yeah. You believe it? Okay. And so x is equal to 6 over root 3. And you might say, wait a second. X is supposed to be equal to 2 root 3. Well, it turns out that this is the same thing as 2 times 3 over root 3, which is equal to 2 times root 3 times root 3 over root 3. You buy that? Everybody buy that? 6 is 2 times 3. 3 is root 3 times root 3. These guys cancel. And so now we have that right there. You could also have rationalized the denominator. But if you did it this way, and this is the answer you got, I'll accept that. That's perfect. You could just leave it right there. That's fine. Now, when you go to check the answer in the back of the book, it probably will have rationalized the denominator. And that's another way we could have done this. You could have said, well, to rationalize the denominator, I multiply the top and the bottom by root 3. That gives me 6 root 3 on the top over 3. 6 divided by 3 is still 2 root 3. No matter how you do it, you end up back here. But if you want to stop and give your answer like that, that's fine with me. But if you're checking in the back of the book, you'll probably want to, if you see, uh-oh, wait, the back of the book says 2 root 3, that's not what I got, do a little bit more work, and that's how you get there. Okay, so that works. We got one that way. Now, how can we relate 3 and y together? Because that's the other bit. So that's how we found x. We said, we'll take the given number with one of the sides. Now we need to take this number with another side. What trig function does that?
Tan.
Let's use tan. I like tan. So we'll say tangent 60. So tangent 60 degrees
It's 3 over y.
is 3 over y. And on the way that I usually deal with this is I just see that. I know that this is some number. I don't care what the number is right now. I'm just thinking, okay, that's some number. And if I just had like 5 equals 3 over y, what would I do? Well, I'd bring the y upstairs, bring the 5 downstairs. So that's what I'm going to do here. I'm going to bring my y upstairs and bring my other number downstairs. Tan 60 degrees, like that.
On the calculator, if you're in radians, will you have to put in the degrees symbol, or would you just...
No, if you're in radians, switch it to degrees. Okay. Yeah. But here's the thing, these are exact numbers. And anytime you can get one that does not involve... anytime you can get an exact measure, get an exact measure. In this case, we can. What is tangent of 60?
1 over root 3. Yeah. Oh no, root 3 over 1.
Root 3 over 1, okay? So that's the same thing as, so I have 3 over root 3 over 1. I don't need to bother with the over 1. 3 over root 3 is the same thing as just root 3, right? By the same way we did that last time. Root 3 is root 3 times root 3 right? Or you could leave it like that. I'm fine with that. If you want to leave it like that, that's perfectly good. But then the back of your book's going to say that, and you're going to go, where did I go wrong? Well, just either rationalize the denominator, or if you could break apart root 3, I mean, break apart 3 into root 3 times root 3. Either way, we end up with the same answer. So exact values. Anytime they say exact values, you're going to be working with one of these triangles that you know. And most of the time, those are the ones we're going to care about. It's just how it works. But you will have to use your calculator for some of them, and it's not bad to know how to do that. Okay, so that's one type of problem you're going to encounter. Here's another type. Everybody got this? All right, here's another type of problem you're going to see. I think this is number 20. Number 20. It'll say exact values. Find exact values for the 6 trig functions of theta, given that, and in this case for number 20, it says cotan of theta is equal to 7 over 24. What? Haha. What? All right, let's think about what is, in terms of a right triangle, and I'm just going to go ahead and start like this. I'm going to say there's some right triangle. Here's theta, okay? So cotan in terms of sides is what over what?
Adjacent over opposite.
Adjacent over opposite. And the way I just checked you in my head was, I know that tangent is opposite over adjacent.
Yeah.
And so cotan is the reciprocal of that. So it's adjacent over opposite. And so that means that this length is what?
7. Yeah, 7.
Has to be. And that means that this length is what?
20.
There we go.
Now
Now you can see I did not draw this to scale, and it doesn't matter, right? But here's the thing, right? That's what that means. Now it could have been scaled. It might have been that was 7 over 24 and that was 1 divided by 7, whatever it would happen to be, right? But this is a triangle that will work for us. And so we're only missing one side in order to be able to answer all of the, in order to be able to find the 6 trig functions.
yeah.
Yeah, and so tell me what to do. What should I write down? 7 squared.
Plus 24 squared equals c squared.
C squared.
Now I'll go ahead and simplify this for you. This works out to 625. Does anybody know what the square root of that is? It happens
16.
to be 25. And so you can see this is certainly not drawn to scale. There we go. From there, I'm confident that you guys could get the rest of them. And let's just see, what's sine of theta?
24 over 25.
Right, because it's opposite over hypotenuse. So opposite over hypotenuse would be that. And ditto for cosine, tangent. And once you got those, you got their reciprocals. So you get cosecant and secant. Questions? Okay, you have a few questions like that. And then we got an application type or a word problem. And this is number 24. I'm going to do a lot of abbreviations here. The peak of Mount Fiji is 12,400 feet. High. That's high. A person several miles away, I'm not going to write all that down, but a person several miles away notes an angle between the ground and the peak.
So 12,400 feet is above ground level?
That's above the ground level. So if you're at ground level, it's 12,400 feet above. And a person standing some distance away measures from the ground up to the peak, and measures the angle at 30 degrees. Oh, that's a nice one. We could deal with that. There will be, I think there's one or two in here that you will have to use a calculator. Estimate distance. Estimate, and actually we could get, well, it's estimate because it's not, that's an estimate. It's not exactly that, but we're going to give it in an exact form. Anytime you have 30, 60, or 90, or 30, 60, or 45, use exact. Just please use exact. But estimate distance. Estimate distance from person to, I'm not going to write this. It says to the point on the ground directly below the peak.
Oh, yeah.
So the point on the ground below peak. So with everything I do, I'm drawing a picture. Here's the ground. Here's Mount Fuji. We know that its height is 12,400. And now what they're asking here is the point directly below the ground level. The person's here, and they measured an angle of 30. And so what we want to do is find this distance right here. In other words, that's what they're asking for. Given that this side of the triangle is 12,400, if that's 30, that is a 30, 60, 90 triangle. This should be a really easy one to scale. We could just scale our regular 30, 60, 90. And what's really nice is, what's that side of the 30, 60, 90? 1. So what do we need to multiply every side by? 12,400. So you do that here and you get 24,800. And then you get your answer by that number times what number? What's the bottom? Root 3. So 12,400 times root 3. Now I haven't looked, but I'm sure in the back of the book it'll give you whatever that is, which is some number between 12,400 and 24,800. Whatever, you could do that. Or you could leave it exact. That's fine too. But another way, let's say it wasn't 30 degrees. If it wasn't 30 degrees, let's think about how we would do this. We would have been given this bit, and we're trying to find this bit right here, given some angle theta. This would be our unknown, let's call it x. What trig function relates these guys together?
Tangent.
So I'm going to say tan theta is equal to what over what?
12,400 over it.
12,400 over x. I can get x by itself. I'm going to bring x upstairs and bring the tan downstairs, just like that. I have my 12,400. And then, if I were so inclined, I mean, whatever that is, if it were 15 degrees, I could take my calculator, plug in 12,400, divide by tan, make sure I'm in degree mode, and then plug in 12, hit enter, and you'd have your answer. Cool? Let's just check. Let's see what happens. What is, so I said that I could do that with anything. This would be then, in this case, would be tan 30 degrees. What is tangent of 30 degrees? Here's 30. Where's my, what are these?
16. 1, 2, 3, 2.
And so tangent is what?
1 over root 3.
So that's the same thing as 12,400 over 1 over root 3. Is that the same thing as what we got? I actually erased it. Yeah, the root 3 comes up into the numerator and we get 12,400 times square root of 3, which is our answer. Questions? Okay, the rest of the stuff is all on the calculator. And it's real easy. Like, it just says, just compute. Like, plug this into a calculator. The only reason I'm doing this is because you guys need to know how to do radians and degrees. You need to be able to switch between them. And so, number 34. says to compute the following, you have sine 45 degrees, b is sine 45, and there's no degree symbol. What could that mean? Radians. The other one is cosine 3 pi over 2 degrees. And the, it's degrees. Whatever it happens to be, it is some measure of degrees. And the other one is cosine 3 pi over 2, but there's no degree symbol. So since you both didn't bring your calculators, I'm just going to take yours, if you will. So for the degree ones, and I'll show this to you. We're in radians right now, and I can see because there's a little rad up on top. So I'm going to go ahead and do the radians first. I'm going to do sine, so I pressed sine, and I'm going to go 45, like that. Sine 45, and in this one, you have a little parentheses that starts there. If I just hit enter, it'll complete it and do it just right. Or if I were so inclined, I could finish the parentheses. Doesn't matter. I do that, and I get this number. So check it out, Noah. Like I said, what I did is I hit sine 45. In that case, I completed the parentheses. You don't have to if that's all you're doing. If this is somewhere in something, and so you're going like 1 over sine something, you might want to complete it. But in any case, it gives us, I'm going to go ahead and round it to 4 decimal places. This gives us 0.8509. 0.8509. Now I'm going to switch to degree mode. Degree, clear. And I can see there's a little DEG at the top. I'm going to do the same thing. Sine 45. What should it be? What should it be exactly?
It should be 1 over
1 over 2.
1 over root 2. Good. Should be able to do... Oh, this is what I love about this calculator. It gives you exact answers. That's pretty cool. So 1 over root 2 is the same thing as root 2 over 2, right? It went ahead and rationalized it for you, right? And we could finish this up. I think you guys know.
I have it. It doesn't give the roots. It just gives like the actual.
And that's fine. That's absolutely fine, right? And in fact, when you go to, if you use that one, and you go to check your work in the back of the book, it's going to be in decimals. And so, yeah, but it doesn't matter. I don't care. You just need to know how to do that. Now, the last type of problem you're going to run into with this is in number 30. I'm just going to do one of them from here, and it's letter C. It says to compute secant of 202 degrees. Now, let me see yours real quick.
You can also just do like sine 45.0 and then just decimal.
Ah, cool. Nice. Very cool. You see that? He did sine 45.0. Now it knows to you when you use, and this is also true in like Wolfram Alpha. If you use a decimal, it'll give you decimals as an output, which is really nice. So, I'm looking at this and I don't see a secant key.
Well, it's the same as a cosine reciprocal.
Oh, so you could just...
But you can convert them all back.
Yeah, so secant is what in terms of...
Hypotenuse over adjacent.
Yeah, but in terms of the other functions, it's the reciprocal of what function?
Cosine.
Cosine. So this is the same thing as 1 over cosine of this amount right here. And so I like, when I'm doing this, you could find cosine of that, and then take whatever it was and go 1 over it. Or you could do it all at once, and that's what I'm going to do. I'm checking that I'm in degree mode. And so I'm going to go 1, divide by cosine 202 degrees, end my parentheses, hit enter, and I get negative 1.0785. A negative. Interesting.
Wait, how does that work?
You'll see. So, everybody got that? That's what it looks like when it's written out. 1 divide by that stuff. And so, That's how you do it. You're like, oh, I don't have a secant key. I don't have a cosecant key. Well, that's because that's what this is. And I would suggest that you do this, like write this out while you're learning this stuff. Don't just straight up compute it. Like, actually write this. I won't fault you if you don't, but it'll be good. Okay, so I think we're ready to move on to our next. Unless there are any questions, that's what your homework is. Then now we're going to move into some uncharted territory. Are you guys ready? Oh, I love your enthusiasm. That's all right. So here we go. The unit circle. We will abbreviate this in this class with a big capital U. And to show that it's capital, I'm going to put these little serif whatever lines on it. The big capital U. That's our symbol for the unit circle. It lives centered at the origin. And guess what its radius is?
Pi.
What's a
Well,
unit?
1.
1. Its radius is 1. That's what we mean by the unit circle. That its radius is 1 unit. This looks terrible. I should do this from the side. Give me a second. Slightly better. Okay. There's a unit circle. So it goes to 1 here, 1 there, -1 there, -1 there. Now, let's take any point on that unit circle. And let's say that that point is, oh, I don't know, how about just x comma y? What equation in terms of x and y does this, what equation can I write in terms of x and y?
Y squared over...
What's the equation? Just the regular old equation for a...
y squared equals r squared.
There we go. X squared plus y squared equals what?
R squared.
R squared. And what's r in this case?
Radius. 1.
Which is 1, so that means it equals what?
1.
1. Now this is, we did this last year, right? There's nothing new here. It's just, that's what it means to be a point on a circle. And we often think about, well, a circle is the collection of points that are true here. Like for instance, 1 and 0 is there. And indeed, is the point 1 comma 0 on the unit circle? Yes. 0, 1 works. Is that? Yeah. How about -1, 0? Yeah, all of those points. Any point in the plane that satisfies this equation will be somewhere on this unit circle. Yeah?
Yeah.
Okay. So let's look at it this way. This is where x is. X lives right here. So in other words, this length right there is what?
X.
X. That length is x.
Oh.
Y lives right there, and so this length right here is equal to what?
Y. So x
Y.
squared plus y squared equals the
C squared. A squared.
Oh, look at that. Look at
We
this.
can
So,
find the
and
radius. Wait, we already know.
what is
1.
the hypotenuse? The hypotenuse is equal to 1. So, check this out. Check this out. Theta. And remember, I said any point on a circle, right? I just happened to choose this. It kind of looks like 45 degrees, but you don't need to think about it that way. But anytime you're on the unit circle, get this. That right there. Okay, so we're taking that bad boy right there. Now, what is sine theta?
y over 1.
Sine theta is y over 1. And like we saw earlier, if your hypotenuse is 1,
Just
why bother writing it, right? What about cosine theta?
1 over 1. No.
X.
X.
Over 1.
Right? Adjacent
Right.
over hypotenuse. And so there's that. So in other words, wait a second. X is equal to cosine theta. Y is equal to sine theta. So check that out. it looks like every point on the unit circle can be written as cosine theta, sine theta. As of right now, though, all we've talked about is that it only works for acute angles thus far. But this is going to give us a way to extend this definition of these functions. We could say, well, for any point on the unit circle, as you start to measure this angle, just take its x value, take its x coordinate, and if you're over here at, say, theta, I'm not going to use theta again. I'm going to say this new angle from here to here is, say, phi. Well, its x coordinate, that is just what we're going to call cosine. Because its radius is 1. The height happens to be positive, so everything's still cool there. So sine phi will be that value right there. If it were all the way down here, and we measured all the way over here, and let's say that that angle is alpha, then whatever this happens to be here, that number is what we're going to call cosine alpha. This number, whatever it happens to be, is what we're going to call sine alpha. And so this will give us a way of extending this beyond a right triangle. So I think you asked about that earlier. Like, we've only talked about it for right triangles. What if we don't have a right triangle? Well, I said day one, we should call this class circles. Because we really don't care about right triangles. Like, what's really going on here is all of this stuff that we're talking about, yeah, it starts with using a right triangle and stuff. But the better way of thinking about all of this is that cosine and sine are points on the unit circle. Now, we're going to come back to this in depth. And in fact, on Tuesday, I'm probably going to go through and say all of this stuff that I just said. I'll probably say it all again. And I'm doing this on purpose. Like, I'm bringing this in a little early so that the next time you see it, it'll sink a little bit deeper into your head. And then the next time it'll sink even deeper until you really believe it. But for right now, I wanted to show you that. And now, let's do... So, since this is true, okay? Does everybody believe this is true? I mean, it just comes from our definition of what sine and cosine are. And if you take any triangle with a hypotenuse of 1, any right triangle with a hypotenuse of 1, you end up with this right here. It's that y equals cosine theta, that x equals cosine theta, y equals sine theta. And since we know that we didn't even need a circle for this, for what I'm about to say, but by the Pythagorean theorem, this is true. It's also the case if it's on a unit circle. We're kind of talking about the same thing. But at any rate, since that's the case, check this out. So x squared plus y squared is equal to 1. Because we're talking about, either way you think about it, any point on the unit circle or a right triangle with hypotenuse equal to 1. And if that's the case, then x is equal to cosine theta. And y is equal to sine theta. And this gives you one of the most useful identities that you're going to see. No matter what theta is, I didn't specify what theta was, right? It could have been anything. It could have been 45. It could have been 1, could have been anything there. And you could see that it's going to extend beyond just the acute case. It could be an obtuse case. It could be a negative angle. We could have taken negative theta right there and ended up down there. You still have a right triangle. You're still on the unit circle, so the x value and the y value, when you square them, still going to give you 1. When you square them and add them together, it's still going to give you 1. Doesn't matter what theta is here. It doesn't matter what angle you're using. Any angle makes this true. And since this is so ubiquitous, like, this is going to show up for the rest of the class. In basically, it's one of the fundamental things that you need to know for this class. There's actually a shorthand way of writing the value of cosine squared. And we write it like this. Cosine squared. Ditto with sine. Sine squared. Shorthand, so you don't have to write all these parentheses and stuff like that, but that is what it means. When you see this, cosine squared, you could think about it as like a new function, like cosine squared.
That's what that 2 meant.
Say again?
That's what the 2, because the other day you had written out like sine or something.
Yeah. That's exactly what it meant. Yep. And this ditto for all the other trig functions. So for instance, if you see cosecant squared theta, that means you take whatever cosecant is, you take whatever cosecant of theta is, and then you square it. Which happens to be the same thing as 1 over sine theta quantity squared. Which happens to be the same thing as 1 over sine theta squared. Which is the same thing as 1 over sine squared theta. Okay, it's just, we're not gonna, the nice thing about this is that you don't need to deal with all the parentheses. That's all that means though. But so many students have run into problems with this. Like, they see this and then for some reason they'll square the input or something. They'll be like, yeah, but don't you square whatever that is? So if it's like pi over 2, then it's like pi squared over 4. No. This means you take the output of that function, whatever it happens to be, and then you square it. And this turns out to be true. I would like to verify this. Well, we proved it. But now let's just check a few values that we know. Okay? I'm going to erase some of this stuff. Am I good to erase this?
Yeah.
All right. So let's leave that up. We'll get rid of the unit circle for right now. We will be talking about the unit circle forever. That is our so central to this class. Almost everything's going to come back to the unit circle. And if you're like, why not any circle? Why don't we talk about a general circle? Well, what is the first thing we did? We took a triangle and we scaled it so that the hypotenuse was equal to 1. We could do that with anything. Let's use our other friend here. Here's our 30, 60, 90, and I'm going to start using these guys right here. So there's pi over 3, pi over 6. What are my bits? Before I scale it, just regular. 1, 2, root 3. So let's scale it down, and let's get it so that the hypotenuse is equal to 1.
Just have to
Divide by 1, multiply by 1 over 2.
Yep, and that leaves me with, well,
1
by design, that's why I did that
half.
there. 1/2
and
1
1/3
half
over
of
2.
root 3 over 2. So let's check this out. Let's say we have pi over 6. So let's do it. I want to show, like, it happens to be the case where right now I'm letting theta equal pi over 6. I could replace that symbol with theta, and we're in the same category. But let's just do this. So either way we do it, if I look at this one and say what's sine of this, you would tell me what? Looking at that.
1 over 2.
1 over.
You'd say 1 over 2. If I said to this one and said what's sine of this one,
1/2 over 1.
which is 1 over 2, right? Okay, so let's do this. Let's just verify this identity. So first off, I'm going to write it out like this. Cosine squared pi over 6 plus sine squared pi over 6. It should be the case, and this is what we want to verify, it should be the case that this thing equals 1. So the first thing I'm going to do is translate this back. Not that you need to do this, but since we're just now learning this, I'm going to do it this way, where we go, okay, whatever, that whole cosine squared thing means you take the output of cosine, and then you square it. So that's what I'm doing right here. I'm being very explicit about that. And so I'm going to square that, and then I'm going to square that. Okay, so what was cosine pi over 6?
1 over 2.
Yeah, 1 over 2.
Cosine?
Oh, 3, root 3 over 2.
Root 3 over 2. Either way you look at it, it's either that one over 1, which is just that. In other words, like we talked about on the unit circle, it's just the x value when you're on the unit circle. That's the x value. The y value on the unit circle is that. Or you could think about it as a nifty triangle, which is the one that I suggest that you keep in your head because that's easier to remember than that. But cosine would be that one over that one. So then sine would be what over what?
1 over 2.
So what's that squared?
3 over 4.
3 over 4.
3 over 4. And what's that
1
squared?
over,
1 over.
which
So
is
just
1.
Yeah.
Oh.
Hey, what do you know? It is true. We could do that. Let's actually, I really want to drive this point home, and we have enough time, so let's do that with some other values here. So remember, this is what we're saying. It doesn't matter what, that's what this means. It doesn't matter what value of theta that you plug in. As long as you plug in the same one in both of them, you can't choose pi over 6 for one of them and then like 3 pi for the other. Like it has to be the same angle. Otherwise, we're not talking about, a point on the unit circle. You're just talking nonsense. So let's do another one. Let's choose theta to be pi over 3. And so that means this is pi over 3. That means this is pi over 3. And what is cosine pi over 3?
1 over 2.
1 over 2, right? Because here's that. It's adjacent over hypotenuse. Okay? And so then we're here. What's sine of this one?
Root 2 over 2.
We're right back where we were. It turns out to be the same thing, right? 1/4 plus 3/4 equals 1. Nice. Now I'm not going to draw it up there. But what is it if I do pi over 4?
Need a 45, 45. 1, 1, 8.
It's
So 1 over 2.
1 over what?
Root
1 over root 2, right? This is the first thing we did, right? Oh, we're just there. And we will be able to finish this example. So what about sine?
1 over root 2.
1 over
Same
2.
thing. And what's 1 over root 2 squared?
2 over 2.
2 over 2.
No. 1 over 2.
1 over 2.
Plus 1 over 2, which is 2.
Which is indeed 1. You can see we're talking about the same thing. This identity, it is a fundamental trig identity. It's arguably the most important one. It just comes from the fact that if you're on the unit circle, no matter where you are, you could think about this a couple different ways. If you're on the unit circle, then it obeys this, and it happens to be the case that x is equal to cosine and y equals to sine. Or you could think about it as, without thinking about the unit circle. If you've scaled your triangle so that the hypotenuse is 1, then this value is equal to cosine. This value is equal to sine. And so it must be the case that by the Pythagorean theorem that this squared plus that squared equals that squared, which is 1. And so then when you do that, you end up with this. And then we will see, we could derive a bunch of cool identities, which we're going to do next time. And then you're going to have to actually have homework on that. And then we'll be going back to the unit circles shortly. So if there are no other questions, you guys are good to go. Make sure you've copied down your homework.